Hi, here we illustrate nonlinear least squares in Mathematica using simulated data. This command here generates a vector of normally distributed variables, and as you can see, the mean is 10, sigma squared is 1, and this tells us the size of the sample. So we have 20 observations. What is written here in mathematical terms is given by these equations. That is, this is just a model with an intercept without a non-trivial independent variable. And I'm writing here that we know the true value of the mean, it's 10, and we know the true value of sigma, it is 1. And instead of this, we are trying to fit this function here. It's a power function. The dependence on x is power. And this example is taken from Doherty's book. And then you can see several commands that program all this. We introduce for the power function this command. And then this is the difference between this, actually the vector of residuals, the difference between given data and what we are trying to fit. The next command, this one, is a scalar product of this y by itself. So this gives us RSS. This is why I am writing here RSS, which corresponds to the power function. And finally, we plot this function, and here a, the intercept changes. I mean, it's not an intercept, it's this factor a changes from -20 to +20, and b changes from -10 to +2. What we get is this surface, okay? And we can see from, if you look at this surface carefully, okay, we see that the minimum is somewhere here, okay? By the way, going back to this example, this function, a power function, can be linearized applying logs. So there is an alternative way of estimating the same a and b. I am doing this just for illustrative purposes. The next example, again, is taken from Doherty's book. The model is the same. That is, we keep our previously generated data, but now we are trying to fit an exponential function. This is why I call this section exponential function, okay? And we want to estimate the number a and b. So we first program everything. This is the function, and then this is the vector of residuals, and then we find RSS, residual sum of squares, which corresponds to exponential function, and plot that function. Here's the plot, okay? It is slightly different from what we had before. I would say it is more regular. And the minimum can be found in stata, which I do later, and it is somewhere here, okay? And finally, this is the what I call symmetric power function, that the model is the same, our generated data the same, but we are trying to fit this equation. And I am doing this in order to illustrate the possibility of having two minimizing points for a and b. So this is the we program here our dependence on x. I put here an absolute value of b because x in general can be negative, and when x is negative, this power may not exist. So for the power to exist, I want the exponent to be always positive. This is why I put here an absolute value of b. So again, there is the residual sum of squares corresponding to that symmetric function that I have. I say symmetric because there is the absolute value. And finally, we have the plot, the 3D plot of that function. And as you can see, there is this clear ridge which separates two regions. And if your initial point is to the left of that ridge, the minimum will be to the left, and correspondingly, if the initial point is to the right of the ridge, then the minimum will be to the right. This is all about illustration in Mathematica.